welcome to everybody to this third webinar. We're going to look at the CPT cone, and I've entitled this "The Ins and Outs of a CPT cone" because we're going to look at some of the characteristics of the outside of the CPT cone, the dimensions, etc., but also go inside to get a better understanding what the CPT cone is all about, how it works, so that you can pick the right cone for the right job. What I want to do in the next 20 or so minutes is really address or give you a general introduction about the CPT cone, and then look at it from three different angles that I've entitled 10 versus 15, compression versus subtraction, U1 versus U2 versus U3. And those of you that are not familiar with CPT, you may wonder why I have picked these titles and what they really refer to. Those of you that have been involved with CPT will have a better understanding why I've picked those, but hopefully at the end of this webinar, all of us will understand what it refers to, what it relates to, so that the conclusion is that with a better understanding of the CPT cone, we can pick or specify the most appropriate cone for the job. So let's first look a little bit about what is a CPT cone. You've seen this slide before if you were in previous webinars with us. On the left-hand side, you see a graphical depiction of a CPT sounding. A CPT cone truck is pushing standard CPT rods, which have a diameter of 36 millimeters, which is 1.44 inches into the ground. And at the end of that CPT rod string is a cone. And you see in a large picture of the cone where we measure the tip resistance, we measure the pore water pressure, and we measure the sleeve friction. That in a nutshell is what a cone sounding or a CPT test is all about. And then you see on the right-hand side a description about how we push it into the ground, and then give a more verbal description of this whole thing. Again, I would like to, even though we've seen this before, I want to look at it a little bit more detail right now and break it into groups to really emphasize what the message is that we are trying to convey when we do CPT. First of all, a CPT test uses highly standardized cone. What I mean with that is that whether you buy an Eijkelkamp geopoint cone or one of our other manufacturers that make CPT cones around the world, the diameters, the length of the friction sleeve, the angle of the cone tip, everybody is using exactly the same dimensions. And the reason for that is very simple. ASTM 5778, which is the American standard on CPT, or the ISO standard on CPT, they use exactly the same dimensions, they prescribe the same dimensions, because the whole process is a standardized process. It also means that we push it into the ground with a standardized rate, 2 centimeters per second or the 0.8 inches per second. And the reason for this standardization is very important. We've been doing electrical CPT now for about 50 years. And by using the same cone, same size of the cone, by using the same speed in which we push the cone into the ground, we have been able to really figure out how to correlate the cone readings with the soil behavior. And if you suddenly start using a different size cone or push it in the ground with a different speed, those correlations may no longer be valid. And that's why it's so important that we're using all these standardized dimensions and push rates. We already talked about what we are measuring. And then finally, we push it into the ground until it reaches the target depth. Now, if you've been told to go to a certain depth, then obviously you can stop then, or when you hit refusal. And I want to mention refusal very briefly, because sometimes the cone doesn't want to go any further. And then you can keep trying, and many people before that have done that. You can also stop doing that, but every now and then people will just think that now they want to go a little bit further, and then you end up with a broken cone. And the reason why I mention this is that a CPT cone is a relatively expensive instrument. It's $3,000–4,000, but it can be damaged. It can break. And so you have to have some respect for that cone, because if you just try to think to put it into the ground, it's not all that smart. We then look at the cone, give the cone tip. You have the friction sleeve, and you see on either side of the friction sleeve this black line, which is an O-ring to give that friction sleeve flexibility, which also means that you have to clean the cone regularly, because if that place where you have those O-rings is going to be full with dirt that is dried up and then caked up, then basically the friction sleeve can no longer move freely, and therefore you don't get accurate readings on your friction sleeve. And then you have your filter element, which in this case is just behind the cone tip. One final thing about the cone tip, to really emphasize again this standardization process. You see here a figure out of the ISO standard with the dimensions of the cone tip for a standard 10 cone that we normally use, but you see what kind of dimensions you have. It's all very well defined. For a new cone, also a slightly worn cone, it shows you what has to be there, the minimum dimensions that have to be there before you have to discard the cone. And the ASTM standard gives you exactly the same dimensions. Again, emphasizing the fact that we are really using a standardized product. So that's kind of in a nutshell what the CPT cone is all about. So let's then move to the first item, which is 10 versus 15. What you see here is a little bit of information about the standard rods again, and to give you an explanation why we're using 10 versus 15, where those numbers are coming from. As I told you before, a standard CPT tube has a diameter of 36 millimeters, which is 1.44 inches. If you take the cross-sectional area of that tube, you end up with about 1,000 square millimeters, which equals 10 square centimeters. And in the time that CPT was developed, we were using the metric system in the Netherlands, so that's why 10 centimeters square was a common classification. These days we probably would have called it, used 1,000 square millimeters, but 10 centimeters square, that's in the cross-sectional area of that cone tube, the CPT tube. And if you then use a cone with exactly the same diameter, then you end up that the cross-sectional area of that cone is again 10 centimeters square. And the base area of the cone tip is 10 centimeters square. Not the surface area of the tip, because obviously it has a much larger surface area, but the base area of the cone tip is 10 centimeters square. And that's where the classification 10 versus 15 came from. We basically look at the base area of the cone tip, or the cross-sectional area of the cone, look at what kind of size it is, and you then call the cone accordingly. Common sizes, 10 and 15 centimeters square, but we'll also have smaller cones, the 1, the 2, and the 5 centimeters square. Those last three, though, are mainly used in the lab or for very special applications, but generally speaking, in the field, we are using either the 10 or the 15. Now, what is the impact of that? How does the 10 versus the 15 compare? First of all, inside the cone is our load cells, and there's a pore pressure sensor, and there's some other instrumentation, inclinometers, etc. And obviously, those sensors need space. And if you have a larger diameter cone, you have more space, not only to house your sensors, but also to put steel around it to make the cone sturdier. And that's why, generally speaking, if you have a larger cone, it is more robust. Larger diameter cone, I should say. Same time, if you have a smaller cone, it really measures then potentially very accurately the soil that you're in right there with your cone, and therefore the smaller cone diameters result in a cone that is more sensitive, and that's what you see here on the screen. This is the equation for the cross-sectional area, and then you see there the common sizes, the 10 and the 15, and the smaller sizes. And then after that, what I showed you was the more robust versus the more sensitive, where if you go larger in diameter, you end up with a more robust cone, and if you go with a smaller diameter, you go to a more sensitive cone. But there's another aspect that is important, and that is to do with the way you can push a cone into the ground and in what depth you can reach. Obviously, when you are going to push a cone into the ground, you have a maximum available push force available. Right? The rig that you're using can only put up so much pushing force. And if you are concerned that you may not be able to reach the depth that you're targeting, then what we found is that if you use standard CPT rods, which have a diameter of the 1.44 inches, 10 centimeters square cross-sectional area, and you use a larger size cone, a 15 centimeters square push cone, that gets you the deepest. So if you're concerned about reaching a certain depth with your rig or with your penetrometer, your pusher, this is the setup that allows you to get to the deepest and have the greatest chances that you reach the target depth. So that gives you a little bit of information about the 10 versus the 15. The second aspect that I want to cover is compression versus subtraction. This crane on this slide, I know it's relatively busy, but what I was trying to do is give some information so people that see the slides without the audio later on still get some of the information. But let's just focus on the chart, the graphs in the center of the slide, and let's look first at the one on the left. What you see there is a cone with a load cell, item number 3, right behind the cone tip. And that load cell measures the load on the cone tip. Above that, what you see is another load cell, item number 1. And to that load cell is only the friction sleeve connected. So you have a separate load cell for the friction sleeve, a separate load cell for the cone tip. You compare that with the one on the right-hand side, you still see a load cell right behind the cone tip, item number 3. But now the friction sleeve is connected to the internal of that cone, and behind that connection, you have a combined load cell, which is designated 1,3, where you measure both the total load on the tip and the friction sleeve. And therefore, to figure out what kind of loading you're going to get on your friction sleeve, you have to subtract the values from both load cells, and that's why we call it a subtraction cone. But that is the difference between a compression cone and a subtraction cone. That's at least the principle. But there's an issue that you need to keep in mind. The load cells that we're using in a cone have a certain accuracy, and then generally speaking, it is 0.5 of the full scale output. And in case of a load cell that can measure the tip resistance, you need to have a reading that goes up to, say, 100 MPa. Half a percent of that is about 0.5 MPa. Now, the other thing that is important to remember is that the load on the friction sleeve is much lower than the load on the cone tip. You can see that in the diagram that you see on the right-hand side of the slide, which is a soil behavior chart, how we correlate the readings from the cone to the behavior of the soil. And you see that the friction ratio goes between 0 and 8%, which means that most of the practical readings we get fall within that ratio, and the friction ratio is, again, the ratio of the stress on the friction sleeve versus the cone resistance. So let's just assume now that we have a soil that is, or a reading that is indicated by this red star, where we have a cone resistance of about 20 MPa, and we have a 2% friction ratio, which means that the stress on the friction sleeve is 2% of 20 MPa, or 0.4 MPa. Well, that is within the margin of the load cell reading. So if you are trying to measure this friction on the sleeve, friction sleeve, you are basically within the accuracy of the load cell if you are using a combined load cell. And therefore, the load cell may not be able to catch it. And that's the problem that you have with the subtraction cone, where the load cells have to be sized for the tip resistance, that it may not be accurately enough or sensitive enough to pick up the sleeve friction, especially when the sleeve friction is relatively low. So what do you end up with? In a compression cone, since you can size the load cells specifically for the job, they are, generally speaking, more accurate when it comes to measuring the sleeve friction, but they're a little bit more susceptible to damage, especially when you load them to relatively high levels. Subtraction cone has a more rugged design, therefore stronger in the field, but may not be as accurate when it comes to the sleeve friction. And again, you start to see that sometimes one cone may be more suitable for a certain job than another job. If you are in an area where you have very low sleeve frictions, you may want to go to a compression cone. If you are in an area where you are more afraid that you're going to damage the cone, a subtraction cone may be more appropriate. So finally, I want to talk about U1 versus U2 versus U3, and then not the rock group that Bono is part of. What do I mean with that? As what you see here on the left-hand side is a small chart there, or a small graphical display of the cone tip with the friction sleeve, and you see three black areas where you could potentially put your friction or your pore pressure filter. You can put it in the cone tip, which is the U1 position. You can put it behind the cone tip, the U2 position, or you can put it behind the friction sleeve, which is U3. So the reason why we are calling it U1, U2, U3 is basically just the three different positions where you can measure your pore water pressure. If you push a cone in the ground, same cone, same soil, then the pressure reading that you get with the U1 position is the highest. It's a little bit lower at the U2 position, and it's again lower at the U3 position. And all that has to do with the dynamic effects. If you're pushing the cone into the ground, you increase the pore pressure because of the dynamic effects, and that gets the cone tip sees the greatest effect there, and therefore the pressure there is the highest. Question then is, what is the most logical place? And people that are familiar with CPT will say, well, I only see it, most of us will only see it at the U2 position. Why is that? Well, there's a reason for that, a very practical reason. And that is what is indicated on this slide. What you see there is the cone with the sleeve, friction sleeve behind it. And what you want to measure is really the true force on the cone tip. But unfortunately, because you have to have this opening for your pore pressure readings, yeah, and then the movement of the cone tip and the friction sleeve independently, there's a small opening there, you get a pressure acting in the opposite direction on the back of the cone. Now, as illustrated here, this is what you really want to measure. This is the true resistance, the true force, the true stresses that are applied on the cone tip. But it's counteracted by this little bit of pore pressure that is on the edge of the cone tip. And that's reflected in this equation. Now you are interested in the true, the corrected tip resistance, but that is then the measured tip resistance plus this correction that is based on the pore pressure at the back of the cone tip. And the pore pressure at the back of the cone tip is the pore pressure at the U2 position. So in order to do this correction, you need to know the pore pressure at the U2 position. And that is why most cones are working with a filtering at the U2 position. Especially when you're working cohesive soils. If you're in granular soils, this correction is not all that essential because the dynamic effects on the pore pressure are limited. The water can relatively easily move away, and therefore this excess pressure can dissipate very quickly. On cohesive soils, though, it may play a major role, and therefore it must be applied. One thing, though, that's important to remember is that if for whatever reason you have a cone that has normally a filter ring in the U2 position. If for whatever reason your client wants to use it at the U1 position, all you have to do is change the cone tip and the filter ring, and you're in business. Measuring the pore pressure U3 position, that requires a different cone. You cannot just easily change something, but U1 and U2 are easily changeable. But again, I would recommend that you use the U2 position unless you have a very good reason to do something else. So with that, we come to the conclusion, and there are really two parts to this whole thing. First of all, what you need to remember is that CPT is a highly standardized test method. And it's important because because of that, can we correlate the readings with the soil behavior. Same time, there is no test method, not even CPT, and I'm a strong believer in CPT, that is the best choice for every application. Now, there is no such thing as a perfect test method. And therefore, there's no cone that is the perfect cone for every application. You should really pick the cone that is the most appropriate for your specific application. And it could be that you want a more sensitive cone, go to a 10 centimeter square cone, or go to a more rugged design, a 15 centimeter square cone with a subtraction application, a subtraction type cone. So you really need to think about what is the most appropriate cone for your job. And we at Eijkelkamp are more than happy to advise you if you have a question about it for your application.
If you have any further questions, again, feel free to contact us and we will answer those as well. We look forward to seeing you next time. Thank you.